This presentation will introduce concepts related to constructing a confidence interval for the difference of two proportions. Note that this presentation is not meant to replace your reading of the corresponding sections in the textbook. While watching this presentation, it would be very helpful if you follow along in the corresponding portions of the textbook. Lastly, please note that you're responsible for reproducing all parts of this presentation on paper according to our course guidelines for formatting of written work, except for any portions that appear in italics, which by the way starts on the next slide, or any slides within the presentation that are specifically identified as not requiring reproduction. Again, as I already mentioned, notice that this slide is all in italics, so you do not need to copy this down. You should, before watching this presentation, have a firm grasp of how to construct a confidence interval for a sample proportion. This video will extend the methods from section 5.2, where we discussed how to construct a confidence interval for a single sample proportion, to apply confidence intervals to differences in population proportions. So just as we saw with a single sample proportion case, the difference of two sample proportions can be modeled using a normal distribution when certain conditions are met. So let's briefly discuss what those conditions are. First, we have what is called the independence extended condition. That condition is met when the data are independent within and between the two groups. Generally, that's satisfied if the data come from two independent random samples or if the data come from a randomized experiment. The second condition that we have to show is met is the success-failure condition. The success-failure condition must hold for both groups, where we check successes and failures in each group separately. When the conditions for modeling the difference of two sample proportions using a normal distribution are met, the standard error of the difference of two sample proportions is given by the formula shown on the slide. Notice that in that formula, P subscript 1 and P subscript 2 represent population proportions, and N subscript 1 and N subscript 2 represent the sample sizes. However, just as we saw for single sample proportion problems, because we rarely know the population proportions, we use the corresponding sample proportions in the formula instead. All right, let's go ahead and now take a look at an example from the textbook to walk through the four-step process to construct a confidence interval for the difference between two population proportions. You will need to reproduce all work associated with the example, starting with the problem statement on the next slide. So from our textbook, we're going to take a look at Guided Practice 6.13. On the slide, you can see the statement for the problem. I'm not going to read through that. You can do that by pausing the video and reading through it at your leisure before proceeding forward. Okay, so hopefully you've read through that thoroughly, and now we're going to go ahead and create a 95% confidence interval for the effect of fish oils on heart attacks for patients who are well represented by those in the study. Also, we need to interpret the interval in the context of the study. So using our four-step process to construct the confidence interval, our first step is to prepare. We're going to identify the sample proportion and sample size values for each sample, compute the point estimate for the difference between the two sample proportions, and then determine the confidence level we wish to use. So in this case, since we're considering the effect of fish oils on heart attacks, then the sample proportion for the patients that used fish oil is calculated. You can see that I've written it in fraction form, and then the decimal value was 112 10,000ths. And the sample size for those people that used the fish oils was 12,933. We then take a look at the sample proportion for people that did not use fish oil, and we see that I've shown the calculation on the slide, and I came up with 155 10,000ths for that sample proportion, and a sample size of 12,938 people. And that again comes right from the table. So we take a look at the difference in sample proportions in this case as our point estimate. You can see the work I've shown on the slide for calculating that, and we come up with a value of negative 43 10,000ths. The last thing we note before moving on from the prepare step is that our confidence level was given in the problem statement as being 95%. Next, we move on to the second step of our four-step process, which is the check step, where we're going to verify the two conditions to ensure that the sampling distribution of differences between sample proportions is nearly normal. So we begin with our independence extended condition. In this case, we can see that is going to be met because the patients were randomly placed into each treatment group. Therefore, the subjects are independent, both within and between the two groups. Next, we check our success-failure condition, and we also see that that's going to be met because from the table, we easily see that the number of successes, that is, subjects that had heart attacks, I need to just make a comment there that that's an odd thing to say is a success, but in the context of this problem, that's how we're labeling it, and failures for both groups were all greater than 10. The last thing that we need to put down on paper when we're doing our check is we then need to conclude by stating, therefore, we can model the difference in proportions using a normal distribution. So our next step in the four-step process is the third one, calculate. If the conditions hold, which we saw that they did in the check step, we then compute the standard error using the sample proportions, find z asterisk, and construct our confidence interval. So I begin by finding the standard error. I've shown the formula and the calculation for that particular value on the slide, and we see that the final value is 145 hundred thousandths. Next, we go ahead and note that the confidence level, being 95%, corresponds to an upper tail area of 25 thousandths. We use that upper tail area with the Arguru continuous distributions calculator probability to values function. The mean is equal to 0, standard deviation is equal to 1. So the upper tail area of 25 thousandths will yield a value for z asterisk of 1 and 96 hundredths. Again, we round that to 2 decimal places. For all z values, we do that. Note, I didn't show how to use the Arguru calculator to find z asterisk in this video because I've done that before already. However, do take note of this bulleted item as to how you would need to write on paper the work done using Arguru by including a sentence just as I did on this slide. We now move to the portion of our calculate step where we're going to form the sketch and construct our confidence interval. We start by drawing two axes, our variable axis, which is the difference between the two sample proportions axis, and the z-axis. And we're going to use the standard error to scale the variable axis. So notice I'm adding units of standard error to the middle value, which is our point estimate of negative 43 ten-thousandths. So I'm scaling it upwards 3 standard errors, rounding to 4 decimal places in this case, and then I'm going to go ahead and scale it downward 3 standard errors. Again, I'm subtracting the standard error from each successive value going downwards. Okay, so that scales the variable axis. Next, I place a blue triangle. Now, this is only for illustration purposes. Typically, you don't need to note this on your sketch, but I'm drawing a blue triangle at the value on the variable axis where the difference of the sample proportions is 0. And we're going to see why I did that when we get to the end of the video. Okay, the next thing we're going to do is include vertical lines going through plus and minus z asterisk on the sketch. I'm going to label those, which I've done on the slide. And then I'm going to shade the interval between those two vertical lines. And I've gone ahead and done that, as you can see on my sketch. Now, although I've shown the vertical lines as being dashed, I did that only for illustration purposes. You should draw those as being solid lines when you draw your own sketches. Okay, next, we go ahead and label the endpoints of our interval, and we're going to add those to our sketch. But before I can do that, first I start by finding the margin of error, which I've calculated here using the formula. I then use the margin of error to subtract the margin of error from our point estimate of negative 43 ten-thousandths. I then get the left endpoint of negative 71 ten-thousandths, and then I add the margin of error to the point estimate to get our right endpoint of negative 15 ten-thousandths. And I then go ahead and label those on the sketch. And that pretty much completes the sketch. On the next slide, I've shown the completed sketch along with 2 ways of mathematically expressing our confidence interval, which you can see in the box. So method 1, where I took the point estimate and add and subtract the margin of error. And then the second one using interval notation, where I show the left and right endpoints enclosed in parentheses. Now that we've finished the calculate step by drawing a sketch, we move on to the fourth and final step of our four-step process, which is conclude. We're going to interpret the confidence interval in the context of the problem. So we can state we are 95% confident that fish oils decrease heart attacks. Let me stop right there for a moment and tell you where the word decrease came from. Remember on the previous slide, our values for the endpoints of the confidence interval were both negative, and that means it implies a decrease of heart attacks in this case. By 15 hundredths to 71 hundredths percentage points, and let me pause again and note that instead of putting the proportion values as decimals, which we had calculated, I'm expressing them as percentages. And that's very common when we write confidence intervals, that we turn proportions into percentages instead. And then parenthetically note that that's off of a baseline of about 1 and 55 hundredths percent, which was the percentage of subjects that had a heart attack from the placebo group, over a 5-year period for subjects who are similar to those in the study. The last thing I want to point out is that in addition, because the interval was entirely below 0. Now let me go back to that sketch again. Remember I put this triangle at 0, and here we see that the confidence interval is completely below that triangle. That's why I'm making this additional statement. Because the interval is entirely below 0, the data provides strong evidence that fish oil supplements reduce heart attacks in patients like those in the study. And so that concludes this presentation.